All right, we are going to go over intermolecular forces here. That is the next unit that we're going to talk about. So if you think about what we've done so far, we've talked about the atom and everything that's going on in the atom, and then we've talked about how our atoms bond together. And now we're going to look at these molecules that we've created and look at how these molecules are sticking together. So we're getting bigger and bigger and bigger. The intermolecular forces are what allow us to have things like solids, liquids, and gases, right? It allows us to have these particles that are stuck together that can form shapes and be different densities. So that's what we're going to focus on. How do we get these things? And the first part of this unit is going to specifically be focusing on how we get liquids and how we get gases, or not gases, solids. And then we'll come back to gases later because they're actually a little bit different. But going to what you already know, gases have the lowest density, right? And if you were to draw yourself a little picture of gas molecules, they'd be all far away from each other. There's no real direction. They're just kind of flying around, right? So there's no definite shape here. Definite shape. Their volume is you can say that it takes like the size of its container, but really if you just look at all the gases in the world, like there's no definite volume to them. They take up whatever space they want to take up, and unless we put them into something, unless it's like you as human beings are forcing them into a balloon or some kind of container, then we can create a volume. But in general, there is no definite volume either. And why is this? This is because they actually have no intermolecular forces. There's no forces holding these gas particles together, right? So they're floating around as their individual molecules. Liquids and solids, on the other hand, do have intermolecular forces because these intermolecular forces are what are keeping those molecules close together. So liquids and solids, liquids are a medium density. You've probably drawn pictures like this before. If you have your liquids inside of a container, they're going to take the shape of the container. And they do have a definite volume, right? I can pour that liquid into something and I can measure it. So it is definite. I can determine it, right? And then lastly, there are solids, and our solids, they have the highest density, and they stay in their shape. They don't need a container to hold their shape. There's my solid molecules there. They have a definite shape. And they have a definite volume. And that is because they have strong intermolecular forces. Okay, so all these intermolecular forces that we are going to look at, these are specific to covalent compounds only. Okay, so these all happen in covalent molecules. We do see that like ions will come into play here, and we'll look at how ions interact with intermolecular forces. So if there's an ion, it's going to be interacting with something that is covalent because covalent compounds have these intermolecular forces. Why do they have intermolecular forces? Well, it's because of Coulomb's law. We love Coulomb's law. You guys know this one well by now. We know that positive and negatives attract to each other. These Q's over here in Coulomb's law equation, positives and negatives are going to attract to one another. And we know that the larger the charge is, the stronger the attraction. So if my charges up here are a +2, -2 versus maybe you have something with a -1 or +1, -1 is what I'm trying to say. This is where you're going to have the stronger attraction because you have greater charges. Okay, so those larger charges are going to create a greater attraction, plus you're multiplying those two numbers together. So 2 times 2 is 4, 1 times 1 is 1. So already that's making a bigger number on the top of our fraction. And then the closer we get those molecules together, right, here's our radius. And if you're dividing by a number, the smaller number you divide by, the bigger number you're going to get. So the closer these molecules are together, the more attraction there is. Okay, so still Coulomb's law. No surprises there. that is causing these intermolecular forces. We're getting, instead of looking at the nucleus or the electrons and where they're going and how they are affecting just the atom itself, we're going to look at what happens when we take Coulomb's law and apply it to two molecules. So the first rule that we have is the London dispersion force. It's also known as van der Waals, so you might see that out in your world. Last year, your teacher probably just called it the dispersion force, but its formal name is the London dispersion force. So this is where we have non-polar covalent compounds. And these non-polar covalent compounds create these momentary dipoles. So they are going to create momentary dipoles that allow two molecules to attract one another. For a moment. Okay, all of this is just for a moment, right? These are very quick interactions between molecules. A reminder that a dipole here is when you have a molecule that has poles, so a molecule with a plus and minus charge, and then if it's a dipole, di means two, so you must have two molecules with a plus and minus charge. And here's my picture here. In normal times, if like everything was perfect, the little electrons would be just hanging out nice equal distance away from each other, but we know that doesn't happen. Electrons are constantly moving, and there might be a moment when all of those electrons end up in the same space, right, in their same area. That's going to create this little partial negative and let the side where the nucleus is become partially positive. That's probably going to make the other electrons in the molecule next to it push away because they don't want to be next to all of these electrons right here. So that's going to become partially negative and this side is going to become partially positive. And for a moment, you now have a positive negative attraction right here. So we've got this little attraction. But as soon as these electrons move, these are broken. These dipoles are no longer in those locations, and this attraction right here is going to break. So these are very quick, very short and sweet little attractions between non-polar molecules. And so because they're very short and very instant, these are very weak reactions, or not reactions, attractions to one another. Okay. Then we have dipole, and my pictures are off, so I'm actually going to switch this. This is going to become dipole. Talk about it down here. Oh, you can't see that. Okay, here we go. Dipole. And this will be hydrogen bonds. Okay, so dipole is when you have a polar molecule, because those polar molecules have those poles, right? So if I have these poles, then I can take my two molecules with my poles on them and stick them next to each other. So here we have HCl. This is a linear compound, but it is not symmetrical, so it is polar, and it is polar because chlorine has all of these extra electrons around it, so it is more negative on the chlorine side, and hydrogen then becomes partially positive. Remember, that's my little partial symbol right there, and it's partial because the electron's not being transferred, right? So it's not becoming fully positive by one and fully negative by one. It's just partial because they're sharing that electron still. It's not like in an ionic compound where we can give it a full charge. So partial positive, partial negative. If I have another HCl molecule next to it, we're just creating little magnets, right? My negative side is going to be attracted to my positive side. And so that is our polar compound, just the positive and negative sides attract. These are like a middle weakness or strength, I guess. And then our strongest, hopefully you can see that in the middle, our strongest version of this is the hydrogen bond. And it's tricky because the word bond is in there, but there are no bonds taking place. They're just attractions. And these attractions are just like the polar ones. They must be between polar molecules. And it's the same idea of a positive and negative dipole. We know that water molecules are polar. The hydrogen side is partially positive and the oxygen side is partially negative. And so it is going to attract to another water molecule. The oxygen will attract to the hydrogen side because that's our positive negative attraction right there. And that attraction is our hydrogen bond. But again, it's not forming a true bond like the bond between these oxygens and hydrogens that are creating this molecule. It's just an attraction. So not a bond. But it's so strong that I believe that we originally thought that this was a bond. So we called it hydrogen bonds, and then we've just kind of stuck with that, even though it really should be called a hydrogen attraction. Hydrogen bonds happen between hydrogen and nitrogen, oxygen, or fluorine, so H and OF. So your hydrogen has to be connecting or attracted to an oxygen, a nitrogen, or a fluorine. If your hydrogen is attracted to anything else, like over here we have a hydrogen and a chlorine, that is not a hydrogen bond, even though there's hydrogen there. It must be between these things. And it's the positive and negative attraction, again, of a polar molecule. And these are very strong. This is why water has like a strong surface tension, right? Because all those water molecules are really bonded together, or not bonded, really attracted to one another. Okay, the last one we have is an ion dipole. And this is where the ion comes into play, but the ion is interacting with a polar molecule. Okay, so an ion has to be interacting with a polar molecule, and this happens all the time in solutions. So this must be in solution. And solutions are generally made with water. So water is polar, right? Here's all my water molecules. Okay, so I don't know if I fixed this, but if we have NaCl here, NaCl is broken down, right? When we put NaCl into water, it dissolves or it dissociates and it turns into its Na plus and its Cl minus ions, right? So it's going to break down into these two things. And what's happening is the water molecules are surrounding these ions by being attracted. Their negative sides are going to be attracted to the positive metal ion, and all of these positive sides would then be attracted to the chlorine ions. So this is how ions interact in a intermolecular force, or with covalent compounds. And these are, I guess, strength-wise, not in our top 3 types of strength, so we won't worry about how strong that one actually is. Okay, so, all right, I'm gonna stop this video here, and then we'll start, and we're just gonna finish up this last section in the next video.